Thank you. Thank you, everybody, for joining this talk today. I'm super excited to be here to talk to you about my vision in my research group for unlocking the potential of planetary-scale machine learning for a sustainable future. So first of all, what do I mean by this? Planetary-scale machine learning. What I mean is being able to take all of this multimodal, enormous, very noisy, very complex data that's being collected by all of these satellites that are orbiting the planet right now and have been orbiting the planet historically, and be able to combine that not just with other satellite data, but even other types of Earth observation sensors like street level images, proximal sensors like drones, in situ sensors, all kinds of different ways we have about recording spatial and temporally reference data about our planet in order to make sense of what's happening on this planet and be able to give information, turning this data into actual information that people need in order to make more informed decisions about this planet using machine learning. And Begum mentioned in the beginning of the talk that I have this role, in addition to being a professor of computer science at Arizona State, I am the AI and machine learning lead for NASA Harvest, and now its more recent sister program that focuses on the US, NASA Acres, which is, both of these programs are essentially trying to enable the use of satellite Earth observation data in agricultural decision-making worldwide and in the US. And in this role as the AI lead, I basically have a front seat to the challenges that people are facing in what we in computer science call the real world, and seeing what are these challenges that are not solved by current methods, where are the gaps, and where do we need to develop better methods for addressing these kinds of problems, and actually have the opportunity to deploy some of these systems in practical use cases. So within NASA Harvest, I lead a project with the Famine Early Warning Systems Network from USAID and NASA that works on providing early warning information for humanitarian response. And this is the kind of end user that we want to be able to deliver this kind of information using AI from the data that we have about Earth observations to. So in this project, basically, FuseNet has the right to ask my team and ask NASA Harvest, what is the impact of a given extreme event X on crop cultivation in some region Y? And they make this request to us for some rapid analysis. And when we get this request, my team goes and does our machine learning things, and we come out with an answer in the form of that event X in region Y corresponded to a change of some percentage or some decrease or increase, whatever the change is in crop cultivation. So this is the format of the problem that we're trying to solve with them. And most recently, over the past year, the region that we've been looking at is Sudan, which has been involved in a civil war for almost a year now, which has been causing much risk of hunger and food insecurity in the region. And many people, there's a ton of reporting about this, how much hunger is being hit in this region. And so what FuseNet wanted to know is normally they would go on the ground to do these kinds of assessments and see what is the state of food security in different regions across the country. But they can't go to this region right now, of course, because of the insecurity. And so they wanted to know from us what is the impact according to this objective source of Earth observation data. And so using these machine learning methods that we've developed, we could estimate that the cultivated area in Sudan in the regions that they were interested in had actually decreased as much as 20 to 30% due to the war in 2023 compared to prior years. And this is pretty much as rapid as we can get today in terms of rapid response from this kind of data. They made this request in around September of last year, and in just a couple of months, we were able to deliver this analysis to them. And so I wanted to give this example to show the kinds of impact that we can have on local and planetary scale challenges using multimodal petascale satellite data. We have huge potential from these data to be able to respond to these kinds of queries. But in order to really unlock the potential that these data have, we need to stop relying on the methods that we get from traditional machine learning and computer vision and think about a new paradigm of machine learning algorithms and approaches that are really uniquely suited to tackle the nature of Earth observation data. So we're really limited, I think, right now by the kinds of methods that we have to be able to harness the potential of that data, because we're trying to take approaches and methods that were developed for a different kind of data and apply these ill-suited approaches to Earth observation data. And I'm going to talk a little bit about this in this talk, but if you want to read more about our thoughts behind this claim, we have a new paper that you can find on arXiv called Mission Critical: Satellite Data is a Distinct Modality in Machine Learning that goes into lots more detail about this. So in order to unlock the capability of planetary scale machine learning, we really need methods that are better able to generalize well to unseen data across space, across time, across spectrum. Right now, our models are extremely brittle. They do not generalize well from region to region or time to time or satellite to satellite even. We need models that are able to perform equally well across diverse geographical regions. Right now, we have lots of methods that work well for some areas, particularly data-rich areas or labeled data-rich areas, and extremely poorly in other areas where we lack that labeled data. And we need to be able to efficiently process this data using our methods. Extremely large models are not great when you have to process petabytes or terabytes of data at inference time, like we do in Earth observation data, where we're getting well over 40 terabytes of data per day from these satellites. And we talk so much about training, but we don't talk as much as we should, I think, about evaluation. So we also need to be able to accurately evaluate how well these models are going to perform, not just before deployment when we're reporting our results in a paper, but also after they're deployed, and be able to estimate how well a model will do in an actual real situation or as things are changing over time and across regions. And for a long time, our field has pointed their fingers at the lack of labeled data as the reason why we couldn't do these things using machine learning. So for years and years, and still today, people are saying, well, if only we had the ImageNet of remote sensing, if only we had the ImageNet of this other field, then we would be able to realize the potential of machine learning in this field. And I think we've seen that that's just not the case. We have had lots of quite large labeled data sets in remote sensing, and it hasn't really turned the tide like people thought it might. And so I think what natural language processing recently has sort of woken the field up to is actually the power of unlabeled data. And if we think about, yes, even though we do have some large labeled data sets in remote sensing, they're still not quite as large or quite as diverse as what we might want. But what we do have in remote sensing unique to this data modality is a truly enormous amount of unlabeled data. The size of these unlabeled data sets that we have is mind-boggling, really, and completely dwarfs what we think of as large in machine learning, typically. So this is just an excerpt from our paper, that mission-critical paper, but in machine learning, GPT-3, which I think we would all consider is a very large model trained on a large amount of data, was trained only on about 45 terabytes of data, and that was about 570 gigabytes after filtering. This is not even what we get in a day from remote sensing data. The Sentinel archive or Copernicus data system has 66 petabytes and growing of data. So enormous labeled data. We actually don't have, enormous unlabeled data. We don't have a shortage of data at all in this field. We just don't really have good methods for analyzing that data. And so what we want to look at now, we have these large language models that have shown us the potential of learning from unlabeled data without requiring any labeled information. And so now, if we can do this for remote sensing data, where we have these enormous unlabeled archives with large Earth models, maybe we can start to better unlock the potential of that data. So I'm a little tired of talking about LLMs. I want to talk about LEMs, or what we call large Earth models, where we can train models on these very diverse data sets of unlabeled data from all these different sensors, and be able to have these pre-trained models that are able to generalize quickly to a lot of different tasks. So not just looking at a single problem like change in cultivated area in Sudan in these years with these defined classes, all of these things where we have such customized specific models that we have to develop to use to answer questions right now, but be able to answer questions about a wide variety of domains, from forestry to climate change to agriculture to development, all kinds of things that we might want to ask from that data. And in the future, hopefully not the too distant future, we hope to be able to start interacting with these data in a way that is more natural to the users in natural language. So somebody would be able to ask of this data, for example, what is the change in Sudan's cultivated area from 2022 to 2023? And instead of having to have these partnerships established, contracts between organizations, defining what the classes of the output is going to be, finding the labeled data, paying the institutions, doing all of this stuff that takes years to develop in many cases, you can just get the answer from asking in natural language. That's the goal that we all want to achieve here. So these self-supervised or foundation models for remote sensing data were a very new topic just a couple of years ago. But today, it seems that just in the couple of days that have passed before today, there's probably been a new one proposed, right? There are so many that are coming out now to be able to take one of these models and fine-tune them in a supervised way using some smaller data sets for different tasks. But if I'm actually going to use one of these models in practice, so if I'm NASA Harvest or FuseNet or some actual end user that wants to benefit from the outputs of these data, if I'm going to make practical use of these foundation models, there's a few requirements really that need to be addressed. So I need this model to not be so specific about what kind of sensor it can use. So I want it to be able to let me use whatever sensors or time steps are available and appropriate would make sense for a given downstream task. So for example, in Hawaii here in the United States, there's a lack of data coverage of several of these data sets. I don't want this method to not work for me now or not be able to use this model just because one of the sensors is missing some data. And of course, I want this to work everywhere in the world. And again, lots of models that we have right now are quite biased in their performance. So for example, this is a cropped out region from France on the top and Kenya on the bottom from world cover. And I'll say world cover is one of the best land cover maps out there. So this isn't to knock world cover, it's just that these methods are all still pretty limited in some of these geographic regions like sub-Saharan Africa, where basically all of the cropland that's shown in this image is miscategorized as shrubland. And I want this model to be small enough for large-scale inference. So performance-related considerations, for example, from the ESA World Serial Project, this is one of the most important considerations for end users. How efficient is this going to be, not just in training, but at prediction time? If I need to use this model to make dense predictions over a very large map, usually in machine learning, we measure inference on the basis of a single sample. But in Earth observation data, we need to actually make a map for those outputs to be useful. So I have to make predictions on millions of samples at a time. And so this means that we need really lightweight models in order to scalably make predictions on those. So maybe we don't want large models, maybe small to medium Earth models. And current models that have been proposed for geospatial self-supervised learning, these foundation models, for the most part, are trained on, at most, data from a single sensor and a maximum of 3 time steps. So we're not nearly taking advantage of all of the different kinds of sensors we have and all of the temporal information that we have from these data. These models also are often trained on quite biased data sets. So some of them are trained on a functional map of the world, for example, which is extremely biased to Europe and the United States. And so as a result, these models tend to be quite biased in their performance geographically. Current models also tend to be extremely large. So if you compare, this is to scale, the parameters that we have in the current deployed model in NASA Harvest for doing cropland classification, which is basically a multi-layer LSTM. It is way smaller than these foundation models that have been proposed, which have 100 million, 300 million parameters. So how can we think about how to leverage the unique character of satellite data to be able to create models that might work better for these end use cases or these end user needs in a practical way? So first of all, we know with our satellite data, we have many complementary sensors. So it's not just that one sensor might be the best for a given task, but learning from these sensors together may also give us some information that makes it greater than the sum of its parts. So we have all this complementary data, but we also have derived products like the dynamic world, land cover data. We have elevation, temperature, these reanalysis data sets, all kinds of data sets, not just the raw observations. And we're collecting this data everywhere on the planet equally. So there's no reason why our training data sets should be geographically biased at all if we're not reliant on labeled data. And we also know that at the resolution of most openly accessible remote sensing data sets, the image-wide spatial context is actually not that useful. So we found in previous work that we may not actually need very deep models because our receptive field being across the entire image is maybe not that useful. Most models are actually not going to learn any kind of spatial relationships in the data. It's probably textural at best. So maybe we don't actually need really deep networks. And so we took these principles about remote sensing data and the kinds of challenges that we were having in practically deploying models in real end use cases and developed what we call Presto, or the pre-trained remote sensing transformer, which we designed to try to fill those gaps. So Presto uses a wide variety of input sensors at pre-training time. So it's not just a single sensor. We have Sentinel-2 multispectral, we have Sentinel-1, we have precipitation, dynamic world, elevation, the location, all kinds of sensors that are in our training data. And we designed our masking in this masked autoencoder architecture. We designed our masking strategies to basically mimic the kinds of scenarios that we'll encounter at deployment time. So we know that we'll have an entire, the rest of the season of data missing if we're trying to do something mid-year, some prediction mid-year. We know that we might have entire sensors missing, or there might be chunks of data missing. So we designed these structured masking tasks specifically for the data that we have. And we also use time series inputs for just a single pixel. And I know that this is very controversial in computer vision audiences and machine learning. People cannot believe that we discard the spatial information, but I tell you, we do. It is only a single pixel. There's no spatial context around the pixel. And we use time series and the multispectral data across all those different sensors. So there's actually an extremely rich set of information in that input, but we don't take the spatial context in this model. That's not to say spatial context won't be useful for some problems, but we find that in a large number of problems, it's actually not as useful as the temporal and spectral dimensions. So finally, we also have a global representation of diverse examples worldwide in our pre-training data. So we specifically designed the sampling globally of the data to try to increase diversity in a variety of different definitions of diversity. And then we evaluate Presto across a wide variety of tasks. So designing the evaluation tasks was as important to us as designing, the specific architecture or pre-training strategies. We really wanted to evaluate how well we could do in a wide variety of data sets and tasks with different numbers of channels and time steps, with different sizes of fine-tuning data, so very, very small to quite large fine-tuning data available. Or a variety of task types, so segmentation, classification, regression, all of those we evaluate on, and a wide variety of geographies spanning multiple continents. So what we find in summary of all the results, I'll go through a few of them here, but the bottom line is that Presto is able to perform competitively to, or in many cases better than, previously state-of-the-art models in all of these tasks, despite having dramatically fewer trainable parameters. So for some of these compared models, we have 1,000 times fewer parameters and perform as well or better on these tasks. So another benefit is that fine-tuning Presto for the downstream tasks is extremely computationally efficient. So we don't have to train thousands of parameters at fine-tuning time. It's very, very small to use the embeddings to fine-tune. And we perform very well when channels are missing in the spectral dimension as well as the temporal dimension. These plots show performance as we add more time steps that we're missing on the left-hand side, as well as when we have only one of those many sensors that were available at pre-training time available. So these results for the TreeSat AI benchmark are when we only have Sentinel-1 or we only have Sentinel-2 available, even though the model is pre-trained and can take in all of those different sensors. And I know I said that we don't use any contextual spatial information, so you might be thinking, well, how do you do classification on images with Eurosat, for example? We do that by basically processing every pixel individually and then summarizing the statistics of those individual pixel embeddings and then using that as the fine-tuning input. And on the Eurosat benchmark, we're able to do better than or close to better than the state of the art using this very small model and encode the images using orders of magnitude fewer flops. Sorry, I don't know German, and I'm trying to get rid of this thing. I'm hoping it was that one. Okay. Okay, so yes, orders of magnitude fewer flops to encode these images and competitive performance. So one of the best things about Presto and why we've had such good end user uptake, for example, World Serials, the ESA project that I mentioned before that considered performance or efficiency at test time to be so important, they are now using Presto. We have many, many people that are using Presto now, and I think a huge part of that is how easy it is to get started because it's so small. And so, these lines here are all you need to start using Presto, and fine-tuning does not require 8 GPUs like some of the previous models, but you could do it on your MacBook, your personal computer in a few minutes. And we are also one of the end users of Presto within NASA Harvest and NASA Acres. So we're now deploying Presto to our different downstream use cases and using it in some really, really challenging contexts where current models just would not work. For example, in a project we have in Maui County in Hawaii in the US where we're trying to map staple crops that are important to Native Hawaiian communities like taro, and we only have like 20 labeled data points of taro, extremely data sparse settings, but creating these maps for the first time using Presto. So I want to end this talk by just summarizing some things that I think we need to think differently about moving forward. In addition to rethinking how the data gives us a different context of information, what kind of inductive biases we might have in these models that are trained on different types of data in machine learning typically. How can we better use this data or better take advantage of this data in our machine learning models if we design for that data instead of hoping the models work in spite of it? We also need to consider, again, things like spatial autocorrelation, temporal autocorrelation, and these different deployed considerations that can have a huge impact on the performance of our models, but can be really powerful if we recognize how to actually explicitly account for those. I think we also need to be much better in the machine learning community about co-developing these methods with end users, not just in the beginning to give us the idea for a project, and not just at the end to say, hey, does this work well for you? So we can put in a case study, but throughout the entire process to actually design things that work well and use those considerations as constraints for developing our systems. I also strongly feel that we need to start considering deployment of these methods as part of the evaluation process. So we know that our metrics are not actually good representations of how these models will perform in practice, yet we keep using them and we report them in papers, and we don't see these methods actually being taken up in practice in a large number of areas. And so I love this quote from Kiri Wagstaff in her Machine Learning That Matters paper that says, to the rest of the world, these deployments of machine learning are the only visible advances of machine learning. These are our only contributions to the world as far as the rest of the world is concerned. So we need to start evaluating if things actually work in the real world. And finally, we need to have these diverse multidisciplinary teams, these pie-shaped people, like Alex said, that can, or these maybe multiple pie-shaped teams that are capable of having all the necessary expertise to develop these kinds of approaches, as well as maybe pie-shaped funding solicitations that allow us to do this kind of multidisciplinary work. So again, unlocking planetary scale machine learning for a sustainable future is going to require us to develop advances that can leverage the unique character of these data and rethink the practices that our community has for developing them if we're going to have the impact that that we have the potential for using these data and using machine learning. So thank you very much. If you want to keep exploring after this workshop, there's 2 workshops that we have on machine learning for remote sensing at the iClear conference, machine learning for remote sensing, and at the CVPR conference, the Earth Vision workshop. Hope to see some of you there. And we'll also have coming out very soon a new data set that we call the NASA Food for Thought Challenge, which is a data-centric AI competition using our crop harvest database for crop classification. That's a partnership with NASA and ML Commons that will be coming soon, and hope to see some participants from here in as well. So thank you.
Thank you very much, Anna. So I think we have time maybe for one question. Okay.
Thank you, Hannah. Yeah, thank you so much for all of this, both like the real world perspective that was very sobering and teaching. I just want to circle back to this one slide you had comparing LLMs to LEMs and your dream of building a model, like following the practice of LLMs, basically to build a large Earth model on unlabeled data. I was just wondering, are we really looking at, if we look at the success of LLMs, are we looking at unlabeled data? Or like, isn't it a problem that basically doesn't need labels? To me, the need, like what labels are, is basically our way to interact with the model, right? It's the way we can query the model afterwards. That's why we need labels at all, I guess. And in language, the language is our way of interacting. Wouldn't the challenge be that if we built a large Earth model, the answer would be 42, and we just wouldn't like be able to talk to the model?
Yeah, that's true, though these models are also fine-tuned in a supervised way for language models, right? So GPT is the pre-trained model on language data that's trained on the Internet Archive, basically. But then GitHub Copilot is fine-tuned in a supervised way, using labeled data to predict useful code, right? So there is still that aspect of labeled data. Of course, some of that could be sort of weakly labeled or unlabeled, but you're right. In the case of remote sensing data, at some point we have to say what it is for a human to interact with it. But right now, we're starting from scratch, basically. Every single time we want to do that, we're having to develop these custom models and build up this knowledge of what's in that data in order to be able to tell the model, what specific thing we want to see. So I think, firstly, we want to get like 99.9% of the way there using this unlabeled data, right? And try to minimize the amount of labeled data that's needed. But I also really want to, even in the future, get away from this idea of labeled data at all and almost move towards custom individual interaction with the data, because like people have all of these discussions in remote sensing about like, oh, we should call this set of land cover labels this, or this other group is like, no, it should be called this. And I'm like, the data does not care, right? It's still the same thing underneath, whatever you want to call it. And so I would love for us to be able to develop systems that get people with language closer to the data, so any individual user could try to interact iteratively with the data at that embedding state, to be able to not label it, but query it using what we might think of as labels, if that makes sense.
Maybe we have time for one more question.
Hey, thanks for the talk. It was really interesting. I would just, if you could comment on what kind of uncertainty do you use for your final products? Because how do you judge that it's good or not?
Yeah, so in the case of the Sudan example, we have, of course, like we don't want to just give one answer that has no confidence or uncertainty associated with it. In that particular project, we do provide standard errors in confidence intervals for telling FuseNet, we're 95% confident that the value is in this range, and we follow established best practices for doing that using, for interacting with land cover data. But in the case of evaluation in general, one of the things I'm most interested in right now is actually unsupervised evaluation. So again, like we talk so much about training and we talk about few shot learning and, we can learn with just limited labeled data. But the problem then becomes, especially for a lot of these downstream use cases, well, sure, maybe you only needed 20 labels to fine-tune this self-supervised model to make a map of taro in Hawaii, but now how do you evaluate that? We don't have labels, right? So what are we going to do here? And that problem is the problem of needing labels for evaluation or needing to evaluate these products is never going to go away. And it's really not feasible, in my opinion, for us to require labeled data all the time for that. And so there's a very emerging area of unsupervised evaluation, or how can we use unlabeled data also to try to estimate how well a model will perform, or even semi-supervised evaluation, not just training, to be able to get a better sense of how models will perform in areas that they haven't seen before.